Hello everyone, and welcome back to Electronics Prepper, the channel where we try to learn as much as possible about electronics to become more self-reliant with technology and prepare for the future. There are plenty of Chinese electronic component manufacturers that most of us don't know anything about, and yet they manage to produce components that might be good enough for our needs. I decided to go ahead and try a few of the cheapest DC-DC converter integrated circuits that I could find on LCSC, which is a well-known, reputable distributor from China. Needless to say, there are many more others that could be good, but since the market is so huge, I just had to settle for some models. And these are the models that I want to show you. What I have now on the screen is a photo of a PCB on which I added some 6 of these models, each of them doing slightly different things. I will go through them one by one and present to you in this video so that perhaps they will be useful for you in the future as well. So, with the help of my general sponsor, PCBWay, I managed to get to test some of these chips. Speaking of PCBWay, please allow me to thank them and at the same time to give you some good news. In case you did not know, PCBWay is a leading PCB manufacturing company that can create PCBs for you, just the PCBs, or they can help you assemble components on them as well, like they did for me with these tests that I've managed to do, both through whole components and surface mount as well. If you plan to create some case or you need some physical object being manufactured, then they can help you as well with CNC machining, 3D printing services, even injection molding, and many other types of creative processes just to help you obtain your dream project. To make things even better, they are currently celebrating their 10th anniversary, and until the end of this month, so for the next one more week or so, you can potentially win some goodies. Okay, you can obtain some exclusive coupons that will basically allow you to give you some discounts for your future orders. They are also offering some fun games. You can obtain some exclusive decorative badges. You can also have the possibility to have your online presence marked on a world map just for fun. For instance, let me just quickly try to show you something from my own country. Right, this is another YouTuber from my own country, and he has uploaded here his gratitude towards PCBWay. If you are feeling generous, they are also organizing charity. So you can buy a special badge for you, and PCBWay will use your money to help others through charity organizations. And last but not least, you may play at a lucky draw and win some even more goodies and even more potential discounts. If you're interested, I will leave you links in the description of this video. Go check them out. Like I said, it's valid until the end of this month, so about 8 more days. Thank you very much, PCBWay, for helping me with my circuits. And now, let's get started and let me show you one by one what I have created. And like I said, this is the overall PCB photo. Now let's take them one by one and see what exactly did I thought about and why did I thought about testing them. So let's start with something simple and something easy, a charge pump. Okay, now some of you might not consider this a true DC-DC converter, but technically speaking, it is a DC-DC converter because, you know, he accepts a DC voltage on the input and spits out another DC voltage on the output. He doesn't need any inductors, any coils, but he does do switching internally. So I have found this particular model, ME2135. This is the root code, so let me mark it with yellow. What comes after 2135 are other subcodes. This kind of integrated circuit comes in two different variants, one that provides 5 volts on the output, a fixed 5 volts on the output, and another model that provides 3.3 volts and has 33 written here instead of 50. Okay, so essentially a charge pump is the kind of circuit that is able to allow you to have somewhat wide range, well, relatively speaking, wide range of input voltages and will give you a constant voltage on the output. Why is this useful, and you know, why this particular circuit? Well, this particular circuit only needs 3 capacitors, one filtering on the input, another filtering on the output, and another special capacitor connected between 2 of the integrated circuit pins. And like I said, no inductor whatsoever, no other components are necessary. This is the perfect circuit that can be used to power an Arduino board or any other boards similar to Arduino, Raspberry Pico, SUP32, STM32, microcontroller boards, you name them. Anything that needs 5 volts, a power supply of 5 volts, consumes less than 300 milliamps, and you would want to power from a single lithium-ion or lithium-polymer accumulator. Okay, in case you did not know, lithium accumulators, whether lithium-ion or lithium-polymer accumulators, have their voltages go anywhere between 2.5 volts when they are completely depleted, up to 4.2 volts typical voltage. So in some rare cases you might find a 4.3 volts lithium accumulators, but for the most part 4.2 volts is the absolute maximum voltage that you should charge your lithium accumulators. So let's say you have a circuit that you want to power with such a single accumulator, but of course you cannot just apply this voltage directly to your microcontroller because your microcontroller needs a constant voltage, right? And the more your accumulator will discharge, the lower the voltage will drop. So you need some form of DC-DC converter. This seems to be a good model, okay? With the other components, so basically with these 3 capacitors, one whole circuit might cost you around 0.14 euros. As we can see, there are more than 6,000 pieces in stock at the day that I am making this video. And only this integrated circuit costs around 7 euro cents per piece. And that's the highest price, considering we buy only a few pieces. But of course, there are volume discounts. The more you buy, the more the price drops. Now, a bit of disclaimer, this approximation, these prices that I will give you are only for your reference. They do not include value-added tax, customs tax, import taxes, or anything else that will basically add up to this price, and in the end they will cost you a little bit more, not to mention the transportation, the delivery service, right, that will also cost. Anyway, these prices are just to give you a rough idea about how cheap they are. So, according to the datasheet, this particular IC model accepts 2.7 volts on the input and from 2.7 to 5 volts. Practically, if you don't care all that much about having a 5 volt fixed output voltage, then I will show you in a moment, because I have a video, a pre-made video, that you can actually work with less than 2.7 volts. And the datasheet says it gives you 5 volts fixed output voltage and 300 milliamps of current maximum. In reality, I made a few tests and I have seen that, for example, if we draw very, very, very small current, like 4 milliamps, in my case, on the output, you can go down easily to 2.5 or even less than 2.5 volts on the input, and you will still get a 5 volt on the output. If you start to draw more, something like 44 milliamps, I tested with 44, then you cannot go below 2.7. That's the minimum voltage that's required for you to still have 5 volts on the output. In case you don't know, 44 milliamps is generally more than enough for powering an Arduino or Raspberry Pico or many other microcontroller boards, because a typical microcontroller board consumes anywhere between let's say 15 milliamps and some 40 milliamps, provided that you don't open Wi-Fi, Bluetooth or other communication devices. For those microcontrollers that do have such a thing, then you will go up to some 100 milliamps, who knows, maybe even more in some extreme cases, but in general you will be able to stay below 40 milliamps, okay? And I've also tested this IC with 150 milliamps, and I get 4.9 volts on the output, at 4.2 volts on the input, and 4.8 at 2.9 volts on the input. Okay, and we cannot go below 2.9 if we are to, you know, still have some an output voltage that gets close to 5 volts. But again, 150 milliamps is not all that it's not a current that you will have to work with quite often. This is the datasheet for this chip. You'll of course find links in the distributors page. Mostly it's in Chinese, but you know, it can be translated, and besides, like I said, this chip is very simple, only needs 3 capacitors and that's it. And according to them, all these 3 capacitors can be 10 microfarads. I chose to put 22 on the input more or less randomly, because I had the 22 microfarad capacitors on other circuits that I will show you soon. So I wanted to have a bit of an extra filtering for no particular reason. Anyway, so let me quickly show you a few things. So this is a pre-made video that I made, and I'm gonna put the table that I showed you earlier. So I was having okay, so on the left side, the multimeter with yellow shows you the output current, 4 milliamps right now. In the middle, you have the output voltage, 4.98 volts. On the right side multimeter, you have the input voltage, 4.7, okay? And I'm going to play back the video, and you're going to see that I basically was playing with the input voltage, and at some point I was also playing with the output current. And you will see, I will jump from time to time, and you will see different values on screen. Basically, the output voltage will be the most important one. Okay, so I have even And this becomes this is where things become more interesting. Even if you drop the input voltage below what they said they will work, the integrated circuit will still work up to a certain point. It's just that you will get a smaller voltage on the outputs. In this case, you know, if you have 2.3 volts on the input, you will have some 4.6 on the output. 2.2 on the input, 4.4 on the output, and so on. But the chip will still work. He will not just disable himself. Well, at some point, of course, the voltage will be just too small for him to do anything. Like 2 volts and you get 4 on the output. Again, with very small output current, so basically no load, essentially. And then when I turned up the output current so to 40 something milliamps, okay, we see that we need to have a higher voltage on the input in order to maintain 5 volts on the output. And that's pretty much it. That's what's more important. Anyhow, just to quickly show you some pictures with the ripple, in case you are wondering, because sometimes the ripple is important. So this was 4.2 volts input, 5 volts output, 4 milliamps of current, which is very, very small, close to nothing, right? You get a roughly 10 millivolts peak-to-peak ripple. Kind of the same at 2.5 volts input. This was with 44 milliamps of load, 4.2 volts input. I would say about 15, give or take, millivolts of ripple, which is still pretty good. 2.7 volts at 44 milliamps output current. Maybe the ripple gets a bit, a little bit bigger, closer to 20 millivolts. And 150 milliamps of current, which is a significant output current at 4.2 volts on the input. Now we see that the ripple is close to 30 millivolts. So, of course, it's a little bit bigger, but for the most part, it's still acceptable. At 2.9 volts on the input, at 150 milliamps on the output, okay, we see we also see some very narrow spikes, and that's pretty much it. Okay, so this was the first model that I tried. Like I said, I would definitely use this when I would want to power a microcontroller board from a single lithium accumulator, and I would not have any other circuit that would draw significant current. Of course, we could have other circuits on the side of the microcontroller, but if we keep the current consumption relatively low, then we can easily use such a chip, such an integrated circuit. Okay, moving on to the second chip that I tested, LP3320. This is a step-up DC-DC converter that requires, well, all the models that I will show you from this point on will require an inductor. But this model of step-up DC-DC converter doesn't give constant voltage, but rather constant current on the output, so we can basically power LEDs from small voltages, okay? The chip himself costs a little over 8 euro cents per piece if we buy small quantities. I would say the entire circuit would cost around 38 euro cents per piece, and he exists in almost 6,000 pieces per stock. So right now, so yeah, he's not gonna go extinct anytime soon. So the datasheet tells us the input voltage must be within 2.5 to 5 volts. and apparently we can have a maximum of 1.5 amps of switching current. The output says goes up to 37 volts, but like I said, this is not a constant voltage but a constant current circuit. Okay, the circuit is pretty simple. Input filtering capacitor, output filtering capacitor, of course an inductor that is connected between the input and the output. Internally, the chip has a MOSFET that is connected from the output pin to the ground, okay, because this is needed for step-up converters. That MOSFET, when he's turned on, he pulls this output down to the ground, which injects a current into the coil. Then when he turns off, the coil will generate a current, which will also generate a voltage across the inductor, which will be in series with the input voltage, and therefore we this way, you know, step-up converters create a higher voltage than the input. Of course, we also need some diode to block the current from coming in reverse, and I have chosen a Schottky diode, 40 volts, 5 amps Schottky diode. And we also need a feedback, one single feedback resistor. Basically, the chip has or requires a voltage of 250 millivolts between the feedback pin and the ground. Okay, so basically the current, this LED is essentially the output of this entire circuit. So here, instead of this LED, you will connect whatever LEDs you have, as many LEDs as you have, provided that you don't go above the maximum voltage that this chip can generate, which theoretically is 37 volts. Practically it's not. I'm going to show you in a moment that it's not. Okay, so this consider that this LED here on the schematic is actually the output. It's your output, and between the feedback and the ground pin, you have this resistor that basically determines the current that will flow through these LEDs through your load. And the formula is very simple: is this feedback voltage of 250 millivolts divided by this resistor. This will give you the current through the LEDs. Okay. Now, in reality, so the circuit is pretty simple. Okay. In reality, because this chip is placed in a SOT23 package, which is a very small package, he cannot dissipate enough power, even though you may, and I did, use enough copper surface connected to the chip and around the chip to try to give him as much heat dissipation surface as possible. And now let me just quickly show you. Okay, this is the PCB, basically made in KiCad. Basically, for all of these, I don't know exactly which one. Let me check. So this was the fifth. Yeah, so the fifth chip is this one. So even though I placed quite a big surface of copper connected to the ground pin, that should help the chip dissipate as much heat as possible, because the chip is very, very small, you know. He's not able to cool himself, really. So we will never be able to get to 1.5 amps of switching current, basically ever. In reality, I could barely keep my finger on this chip when I had 0.8 amps on the input. Again, it's not the output current that matters, because after all, the output current is constant. The input current varies based on the output current and the output voltage that we will allow to happen. Okay, the more LEDs we will connect in series here, then the bigger the voltage this chip will need to generate for the same output current, and therefore the bigger the input current he will have to draw, because the input voltage is constant. Okay, so we have constant voltage on the input, therefore the current must be variable, and we have constant current on the output, therefore the voltage will be variable. Okay, so I would not recommend that you use this chip in a way that he draws more than 800 milliamps maximum on the input. And really, we can go to the data sheet. This is okay. This is the chip low power semi 3320. Okay, constant current switching for, they say 11 pieces white LED, but in reality, it depends a lot. Depends on what the voltage of the LED is. They, like I said, they say output voltage up to 37 volts, but practically, I will show you that you cannot get more than 27 at best. And actually, at 0.8 amps, the maximum current that I recommend, you will only get 16 volts on the output. So yeah. Anyhow, or at least in the tests that I've made with 200 milliamps of output voltage, but I somehow don't think that's a limitation. Anyway, the idea is that if we go in the datasheet somewhere down in the table, we see MOSFET on resistance 400 milliohms. Okay, and this basically tells us approximately what's gonna be the maximum input voltage, because the dissipation power essentially is this input current. Sorry, I said input voltage, I meant input current. So the dissipation power is given by the input current squared multiplied by the MOSFET on resistance. Okay, because it's the current that flows from the input into the coil output down to ground through the MOSFET. Okay, so at 0.8 amps we have 0.8 squared, so multiplied with himself and multiplied with 400 milliohms, we get 250 milliwatts of dissipated power. And this is really what this chip is able to dissipate. Again, in SOT23 package, this package is just too small to be able to handle more. Okay, or he will be able to handle more, but the temperature will go up significantly. At 0.8 amps, 250 milliwatts of dissipated power, I could barely hold my finger on the chip. So I would say, you know, my personal resistance threshold is somewhere around 50 degrees Celsius, give or take. So if I cannot hold my finger on the chip, it means that the temperature has gone above 50 or 60. At 60, I don't really have the ability to hold the finger too much on a component. So definitely the chip will go above 60 degrees, and yeah, you could push this limit higher, closer to 100 something degrees, but you know, I wouldn't recommend it. They say that over temperature protection starts to happen at 160 degrees Celsius, but needless to say, you know, it's not recommended that we go quite that far. And this is okay. Let me show you the video with the tests that I've made. So on the left you have the input current, currently 0.28 amps. In the middle you have the output current in also in amps, so 180 milliamps, and on the right side you have the voltage One thing that I forgot to mention is that when I tested this chip, of course I didn't wanted to put white LEDs as load. I wanted to, you know, play with the output. So instead of a LED, I placed a resistor. In principle, anything below 180 ohms, if you want to have 200 milliamps of current flowing through here, you know, I've calculated that anything below 180 ohms of resistance should be placed instead of these LEDs and will be fine. The lower the resistance, the lower the voltage that will be generated for what would be the LEDs. The higher the resistance, then the higher the voltage would go. And this is how I basically conducted my experiments. Okay, this is why on the right side right now you see 6.3 volts. That is the voltage across that resistor that replaces the LEDs. Okay, and on the outside of this screen I have a resistance decade box, and I was playing with that decade box. I was increasing the resistance from 30 ohms upwards. So earlier you saw 30, now what we have on the screen is for 40 ohms, and then I kept increasing from 10 to 10 ohms. Okay, and we see that the input current increases, the output current remains relatively constant, which is good up to a certain point. The output voltage will also increase. So now we've reached to 14 volts and 680 milliamps on the input. Now we've reached the limit that I say, you know, we shouldn't really go above 800 milliamps on the input, 16 volts on the output, 200 milliamps of current on the output. I chose 200 milliamps more or less randomly, okay? And then I went upwards, 900 milliamps on the input, 18 volts on the output. At some point, for some reason, the integrated circuit, like here, so at some point the integrated circuit couldn't give me 200 milliamps on the output. So from time to time you might see different current here in the middle on the yellow multimeter. 1.1 amp on the input, 21 volts on the output. And yeah, at some point you will see, and let me see if I can just jump forward a little bit. I was actually pushing him towards 1.2, 1.3 amps input current, and it was kind of starting to turn on and off. Let me see if I can find that moment. Yeah, here. So I reached almost 1.3 on the input, and amps on the input, and where was I? Just a second. Anyway, the over temperature protection started to hit. Oh, here it was, because I wasn't playing with this as much. You see 1 point something amps and then drop again. Yeah, so there's just absolutely no way. I'm kind of having a problem finding that moment precisely, but anyway, there's just no way we can take this all the way to 1.5 amps on the input. No, absolutely no way. So that's the chip limitation. Anyway, all in all, it could be a good enough solution. When we have a low voltage on the input, like 5 volts, we may encounter, we have, you know, something powered from 5 volts and the power supply is strong enough to be able to give us a 1 amp extra current on top of whatever we are powering. And for some reason, you know, we may need some lights to turn on or whatever. This is a good chip to have. And if you think about it, he can power quite a bit of quite a few LEDs, like you know, 16 volts multiplied by 0.8 amps. No, sorry. 16 volts on the output multiplied by 200 milliamps. That's 3.2 watts of power. But you know, if you think about it, a single LED consumes I mean, it's powered from, let's say, 3 volts and consumes, I don't know, maybe 60 milliamps or something like that. So 0.18 watts. So 3.2 watts divided by 0.18, you know, we could add 17 LEDs like those, which would make quite a bit of light. So yeah, all in all, this seems to be a nice enough chip to perform this task. Moving on, another step-up converter, but this time I don't know how I should call this, a classical step-up converter, one that actually gives us constant voltage on the output. MT3608, okay? And so this exists, apparently this is a hot component. He exists in 260,000 pieces in stock, quite a lot. The price for the entire circuit that we would create would also be around 36 euro cents. The price of the chip for the smallest quantity is 7 euro cents. And of course, at higher quantities, the price goes down. According to the data sheet, he accepts input voltage between 2 and 24 volts. The output is a bit unclear how much it can go. Well, actually, we will take a look in a moment in the data sheet. Up to 28 volt output voltage. But what is a bit unclear about the output is whether, well, at least in terms of theoretical values, is whether they say 2 or 4 amps maximum current. Because if we take a look at the data sheet, here on the left they say internal 4 amps switch current limit. And here on the top right they say 2 amp step-up converter. And of course it's a bit unclear which is which. But well, it was unclear for me, but now things are clear, and this is why I'm you know, presenting to you this chip, because I have tested this, and apparently 1.8 amp maximum switching current is what you should be injecting into the integrated circuit. So I have tested this, since this is a step up. I have tested this in possibly the most common way we might use this chip, with 5 volts input, wanting a 12 volt output. Now I got only 11.4 volts due to these 2 feedback resistors. I could have tuned them to actually get 12 volts, but I didn't care about exactly getting 12 volts. You know, these 2 feedback resistors, which in my case are 180k and 10k, these are basically setting the output voltage. This is essentially a standard step-up converter, just like with the previous circuit. You know, we have input filtering capacitor, output filtering capacitor, 1 inductor. I didn't know exactly what inductor I would want, so in my test circuits I created the boards with 2 different inductors and some switches, some jumpers to be able to, you know, connect one inductor or the other. And I have tested both of them, and I will show you both. A Schottky diode, of course, to block the reverse current, and two feedback resistors that essentially set the output voltage. Okay, with 5 volts input, wanting 12 volts or almost 12 volts output, I was able to have a maximum of 700 milliamps on the output, which, doing the calculations in reverse, assuming 90% efficiency, you know, this means a 1.8 amp input current. And at this input current, you know, the chip gets hot that you can barely hold your finger on him. And really, this was the way I was, this was the only way I could test the temperature of these chips. This is also a SOT23 package, so a very small chip. Sadly, in order to accurately measure temperatures for these kinds of very small chips, I would need to have one of those infrared thermal cameras, but I don't. And I have only an electronic thermometer, but the problem is, when you put a thermometer that has, you know, a very long metal body on the body of the chip, which is hot, they will of course reach a thermal equilibrium, and while doing so, the thermometer will suck quite a lot of the heat from the chip, essentially cooling this chip, and basically he will show you a smaller temperature than what is actually experienced by the chip normally. So there's no way you can measure temperature accurately with contact methods. You need to use a contactless method, but I don't have one, so I just use my finger to, you know, approximate how hot these chips were. So again, I would not recommend more than 1.8 amps on the input, and the output current, of course, will depend on the output voltage. The closer the two voltages are, input to output, the more current you will be able to draw from the output. And the farther apart they are, then the less current you will be able to draw. Okay. To show you a few waveforms with the ripple. So this is the first tests that I have made were with the 22 microhenry inductor. This was at no current whatsoever. The ripple is about 150 millivolts peak to peak, and it's a relatively low frequency ripple of 145 hertz. Okay. The moment that we start to draw some current, then the ripple goes at a higher frequency. I remind you that this chip says works at 1.2 megahertz. So at 100 milliamps of current and the same 22 microhenry inductor, then the ripple goes down to some 50 millivolts peak to peak, more or less. This is 500 milliamps of current, and we have some, I don't know, 150 millivolts or so. 700 milliamps of current. I'm of course talking about the input current, and the output ripple is also around 150 or so millivolts. And then I switch to 10 microhenry inductor. At no current whatsoever, we see also about 150 millivolts of ripple current, but this current will basically of ripple voltage, sorry. But this ripple voltage will tend to vary. It will not be something constant. At 100 milliamps, we will see some 30 millivolts peak to peak or so. At 500 milliamps and the same 10 microhenries, we will have 70, 80 millivolts, ignoring these peaks, these very narrow peaks. But mind you, this is we have 500 nanoseconds per division, so this is indeed a 1.1 megahertz chip. So theoretically, we could potentially, you know, just filter these out with a further filter connected to the output. And this is 700 milliamps with 10 microhenry, which is more or less the same. It seems to be a slightly bigger ripple, something like 120 millivolts. Yeah. So this was the third chip that I tested. Let's move on to the last three, which are step-down converters. This is a step-down chip that it comes in small outline 8-pin package with an exposed pad. So because the package is bigger, all of these from before were SOT23 and the ones that I will show you after, but because this is a bigger package, small outline 8, and also has an exposed pad, thermal pad on the back, you know, we are able to dissipate more heat into the PCB, and therefore this chip MT2499A is able to work with somewhat higher currents. This is a step-down converter. The entire circuit made with this chip costs about 0.43 euros. The chip himself at small quantities cost about 13 euro cents, and we have some 37,000 pieces in stock, so again can be easily found on the market. The datasheet says input 21 volts maximum and output 3.5 amps maximum. Practically that's not really the case. Yes, the chip does have better ability to dissipate heat, but I could not take him more than 1.9 amps maximum. Tested with 12 volts in and 5 volts out, which is the inverse of what I tested for this step-up converter. It's practically what I think would be the most common way to use a step-down converter, wanting to step down from 12 volts to 5 volts. I could not get him above 1.9 amps without getting him so hot that I cannot leave my finger on him. So yeah, we could theoretically go up higher than 2 amps, but like I said, we would get a bit too close to his maximum temperature. The schematic is also pretty straightforward. An input capacitor, a couple of output capacitors. This was what they recommended in their own datasheet, 22 microfarads times 2. I just, for the most part, I respected the data sheets that they provided, you know, when I had sufficient informations. We also need a small bootstrap capacitor, 22 nanofarads. We see this here between the bootstrap pin and the switching pin. 22 microhenry inductor and a couple of resistors for setting the output voltage for the feedback. Okay, I highly recommend that you read, regardless of what chip you want to use. I highly recommend that you read the data sheet, because some of these chips, like this one, for example, have some particular requirements in terms of what these resistors values need to be, at least one of them. Okay, in order for the chip to maintain himself stable in operation. For example, for this particular chip, in the datasheet they said that this upper feedback resistor should not be lower than 100 kilo ohms. So this forces you to calculate the other resistor based on this upper value resistor and whatever voltage you want on the output. Okay, and for me to have an output voltage close to 5 volts, give or take. You know, for me, I necessitated a 22 kilo ohm resistor, and that's pretty much it. That's the entire circuit. Let me show you. So this is number 2. Let me show you some ripples. Okay. I had a bit of a problem with testing this chip at higher currents. I have a rather primitive self-made electronic load that sometimes can generate some oscillations, especially if we use longer cables between the output of what we are testing and the input of that electronic load. So I made 2 tests, one with that electronic load and another set of tests with a dummy load that is just a collection of resistors, essentially, that don't oscillate because they have no way of oscillating. So with the electronic load, this is how the ripple looks like at no current whatsoever on the output. Some 80 millivolts peak to peak or so. At 100 milliamps output current, which is relatively small. Also some occasional 80, generally within 50 millivolts or so. Half an amp, I had some smaller ripple, so I have 20 millivolts per vertical division, so I would say around 30 millivolts peak to peak, okay, with the electronic load. And then at 1 amp I even had smaller, even smaller ripple. Well, I think also around 30 millivolts, give or take. Then I had to switch to a dummy load that you know, doesn't have an op amp and other circuits and cannot oscillate, cannot generate my circuits to oscillate. So with this dummy load at 800 milliamps of output current, I kind of noticed a bit of an oscillation on my chip. But still, you know, it's not all that bad. Some 300 millivolts at 37 kilohertz. But then when I increased the current, for example, at 1.5 amps, this oscillation disappeared. So I'm willing to believe yeah, it's not a problem of the circuit, it's more a problem of, you know, how I was testing everything. So at 1.5 amps output current, I was having only some, I don't know, 30 millivolts of ripple peak to peak, which is pretty good. And at 1.9 amps output current with the dummy load, the ripple went up again to some 100 something, 120, 130 millivolts peak to peak, and again having a more sinusoidal waveform. Not bad. It's just something, you know, we need to be aware of. Okay, and last but not least, I have 2 more step down converter models that in essence are identical in the way they work, in the circuit that needed to be created. So I will tend to present them both to you more or less at the same time. I have an ever analog EA8212 step down that costs, the chip himself cost 8 euro cents for small quantities. We can find him in over 31,000 pieces in stock. The entire circuit would cost about 38 euro cents, so still pretty cheap. The datasheet says 18 volts maximum input voltage, 2 amps maximum output current. We cannot get there. The reality is that I could get up to 1.5 amps. It's not bad considering it's a SOT23 capsule. I've tested this with 12 volts input, 5 volts output, again something standard. 1.5 amps, I would say we should not exceed 1.5 amps maximum output current, and pretty much the same. So let me just quickly show you a little bit of the data sheet as well. So ever analog EA8212, okay, 18 volts, 2 amps, 500 kilohertz synchronous buck converter. I haven't tested the efficiencies as well. Some of these claim to go very high, up to 96 or even 98%. And there's another one that basically is identical but manufactured by someone else, MT2492, also in SOT23 package with the exact same pinout. This one seems to be a bit cheaper, only 3 euro cents per piece at smaller quantity for the chip himself. And with the other components, at least the components that I chose, you know, the circuit goes up to some 33 euro cents. We can find this particular chip in in a ridiculously large quantity in stock, or almost 500,000 pieces. So yeah, we should be able to easily create such a circuit. They say input 16 volts maximum. This other one was 18 volts. Output 2 amps maximum, but again, I couldn't go up to higher than 1.5 amps without making him get so hot that I just couldn't keep my finger on him. Again, the circuit is as simple as the previous one: an input capacitor, 2 output capacitors, a bootstrap capacitor that for these models they appear to be needing a slightly smaller, a slightly bigger one. Here we had a 22 nanofarad. Here they say 33 is needed, but anyway, an inductor 10 microhenry and a couple of resistors that form a divider to, you know, feed the feedback pin to set the output voltage. Again, just like with the other chips that I've presented to you in this video, do read the data sheet carefully, because you know, they will at some point they will mention that the certain one of these two resistors need to be of a certain value, or higher or lower. For example, for this model MT2492, okay, at some point they say choose resistor 1. By the way, resistor 1 in their schematic is this upper one, okay, in the feedback resistor divider. Choose resistor 1 to be around 100 kilo ohm for optimal transient response. Some other and they also mention, and some other manufacturers also mention this, that the feedback resistor 1 also sets the feedback loop bandwidth with the internal compensation capacitor. So what they don't, some of them mention, some others don't mention, is that setting a wrong value for this resistor will basically create an unstable circuit for you that will potentially oscillate in certain conditions, okay? So yeah, they also mention for some of these chips that you might add an extra compensation capacitor here in the order of some picofarads across this resistor, but they also say it's optional. I didn't add him. Apparently, I don't really need to. Okay, and let me quickly show you some ripples for these two models. So EA83, this is at no current whatsoever, 0 amps, so it's like 10 millivolts give or take. This is at 200 milliamps output current, around 15, maybe 20 millivolts, peak to peak with some bigger spikes, but that are still relatively acceptable. 500 milliamps output current, again some 20 millivolts ripple with a few sharper peaks, and 1.5 amps output current. 50 millivolts per division, so we have also around 20 millivolts of output ripple. So the output ripple is pretty good, especially if we can ignore these sharper peaks, or if we can filter them afterwards. The results are pretty nice. Now let me show you MT2492, which for all practical purposes has similar results. So here I had no current drawn whatsoever on the output, 5 millivolts per vertical division, and I had some, I don't know, 15 millivolts peak-to-peak ripple voltage. At 200 milliamps, some 15 millivolts of ripple voltage and some spikes. 500 milliamps, again some 15 millivolts and some spikes. 1 amp, I would say I had about 20 millivolt peak-to-peak and some spikes. And 1.5 amp, pretty much the same, 20 millivolts and some spikes of ripple. And that's pretty much it. And I've reached 1 hour video. I think I've talked enough. So these were 6 models of integrated circuits that I have tested. I would definitely be able to use them if I don't need higher currents, if I don't need higher voltages, if I don't care about one of these chip burning himself and me just replacing the entire board. I mean, it's not that you cannot desolder these manually and replace them. It's just they are a bit of a pain in the ass to do so at home. Anyway, all in all, these were nice chips that I managed to find. So I hope this video was useful. Just to quickly show you the inductors that I've used. So for these, for all of these circuits, well, with the exception of the charge pump that I showed you in the beginning that doesn't have any inductor, for all of these other circuits, I have either chosen 10 microhenry inductors or 22 microhenry inductors that can resist up to 5 amps. Technically speaking, it wasn't really necessary, but again, I had no idea. I just wanted to be safe and not have inductors that would saturate at the currents that I was going to use. So I chose these 5 amps inductors that basically cost around 22 euro cents per piece at the smallest quantity and can be found in 4,000 or 3,000 pieces in stock. I will also put you a link in the description towards these inductors, but of course these are just for reference. In practice you can choose whatever other inductors you have. Just make sure that they will be able to work with these high frequencies, because most of these chips work with high frequencies. 600 kilohertz this one, 500 kilohertz this other one, 340 kilohertz this other one, 1.2 megahertz. There are quite a few that nowadays work at 1.2 megahertz, 1 megahertz or even above. 1 megahertz fixed frequency switching the circuit for LED. Okay, even the charge pump works at 650 kilohertz. He doesn't need she doesn't need an inductor, but she still works at pretty high frequencies. So yeah, anyhow, thank you very much for watching this video. I hope you learned something new. I hope this was useful to you. As a final thought, I would definitely say that instead of buying all sorts of DC-DC converter boards already made, already placed on the market, that I have no idea what chips they use, I have no idea how good they are, and I see them, especially in my country, in the local distributors that just go and buy tons of Chinese products, but they don't really care all that much about what they're buying. Instead of buying those shitty products, I would definitely go for a circuit like this with one of these one of these integrated circuits that you know, we could test and see that they are good. So anyhow, that being said, I believe I have shown you enough. Thank you very much for watching. Thank you very much for those of you who are supporting this channel on Patreon. I will upload soon a video concerning the future of this channel, and I will explain a few things. Thank you again, and I will see you soon. Bye bye.